Hello, everyone. I'm very excited to have you here today with me, and welcome to version 1.0 of the Metaverse. Um, so I wish I could be there in person, but I'm still happy to join you virtually. For those of you who doesn't know me, my name is Inbal Levi, and I have the slides for the presentation here. You can scan the QR code or go into the link described. And I would really love it if you could look at the slides live, because there's some code snippets and code examples, sorry, on the slides. So it'll be great to have you experiment with them. Again, nice to meet you. If we haven't met before, my name is Inbal Levi. I'm a C++ software engineer and OS internals engineer in Microsoft. I'm also an ISO CPP Foundation and Boost Foundation board member of the ISO CPP committee as Israeli National Body Chair and Library Evolution Workgroup Chair. So if you're not familiar with the term Library Evolution is the group within the standard that is in charge of the design of the standard library, C++ standard library. So to explain to you a bit about this process of ISO, basically the flow of a proposal to ISO of a new feature is as follows. So we have here in green, dark green are active study groups. Light greens are dormant ones. The study groups are basically the first stage for a proposal to land. Of course, you could get, let's say I have a new feature, reflection. You could get an early feedback from people, but basically this is the first, let's say, official discussion. And the groups are split into topics. And for example, for reflection, it landed into SG7. So SG7's full name is actually compile time, but here it says reflection, well, close enough. Definitely this group have been dedicating its time to reflection lately. Um, so our proposal lands in SG7 that gives initial feedback on the paper. And the next stage is for the proposal to go to core evolution. It's called language or core and library evolution. So in the case of reflection, as it have a quite significant number of stud metafunctions inside of the stud namespace, we got, of course, the proposal going through our room as well as evolutions. So as I mentioned, I'm Library Evolution Chair. That means that this design group is the one I'm mostly attending. Next stage of proposal is, as you can imagine, go to library groups. And reason is that at the end of the day, the ISO standard of C++ is a document. And the way to put features into this document is not by implementation, but by specification. So we have the proposals, and those are phrased in wording, what we call standard is. And those wordings are basically the way that you push something into to this document. So after a feature design have been finalized, we can get to the wording groups, library wording or core wording. Core is again the language, and by the next step, the proposal is being voted in plenary. So reflection proposal, happy news. I'm sure you already heard that probably in Herb's keynote, but reflection proposal have been voted this Saturday into the C++ 26 draft. This is not final, of course, until the last minute things can change, but that makes that it's very, very, very likely that we'll get, and by the way, it was voted with very, very large majority, so it's very likely that we're going to get reflection in C++ 26. So it's pretty exciting. Yes, so as I mentioned, we have reflection voted into plenary. So what do I mean when I say reflection? Reflection is basically the ability of a software to expose its internal structure. And when I talk about reflection in C++, I talk about static reflection. So the compiler exposes structure at compile time. So you might be familiar with reflection from other programming languages like Python, for example. It's a different aspect of reflection, because in Python, the interpreter can basically, by reading the syntax, can inject the information, extract the information from the program and present this for usability. But here, when I talk about C++ reflection, it's something that the compiler is actually doing. So let's say I have a C++ program and it have reflection syntax. The compiler goes over the reflection syntax and translate that into a regular C++ program. So now we have a regular C++ program, and this is being compiled by the compiler. And in the final binary, there's no traces of the fact that this information, this instructions have came originally from reflection. So it turns into regular C++ code and then later instructions. So it addresses, of course, concerns like security or safety, etc. Unlike reflection in runtime that we can observe in other languages. By the way, Rust, of course, also have reflection, and I'll address this a bit towards the end of the presentation. So yeah. When we talk about reflection in C++, we talk about static reflection. The compiler exposes the information and compile it. So this talk have two parts. First part is intro to reflection. We're going to go over a brief history of what we have had in reflection so far. We're going to look at the latest proposal. That's the one that actually been voted into the standard on Saturday, P2996. And at that point, I also want to emphasize thank you for all the authors that have been working on this proposal. I think it's really amazing that we managed to get this, and I think it's a really great tool. And I hope by the end of the talk, you're going to be convinced, as I am, of the power of how powerful this tool is. So yes, after the proposal, we're going to look at some usage examples. And as I mentioned, as Library Evolution Chair, I have my focus and interest is on reflection-based libraries and how they're going to look like. And I'm sure we're going to get quite a significant amount of them in the future. Examples also in this talk are from P2996, P3096, and EDG's implementation. So I also want to point out Dan Katz for implementing reflection in Clang, which is available in Godbolt, and White Child, with also implemented this for EDG, even before actually. And thank you very much to both of them for basically enabling us to already use this feature, despite it only being voted on Saturday. Already have some experimental, of course, but still implementations on Godbolt. So this what and it allows you even to experiment with this during this talk, during this very talk. Second part of our talk is gonna talk about the impact of reflection on code bases. So we have, I would talk about reflection as customization point and explain this term as well. We'll look at what the meaning of reflection in pipeline and how it's gonna change our CI, and talk about what next in this realm. So let's start with a brief history. In 2006, first place I found for mentioning reflection was by Matusz Kolczyk in the scope of the standard, of course. And Matusz had a mirror reflection library that he wrote. Now, what you might be familiar with in terms of template metaprogramming and type traits is what this library is. Sorry, so we try to reflect on our code using template metaprogramming. In 2012, we had a paper from Mike Spartus. Mike Spartus, by the way, have been part of the committee for a very long time and have a very interesting perspective. So he wrote a paper trying to enumerate the use cases for compile time reflection. And he mentioned things like serialization, delegation, getters and setters, and customization point. He didn't call it customization point exactly, but that was the intent. And I will maybe talk briefly later during the presentation on whether we covered all the use cases here, but I'll give you a spoiler that the is not all the use cases here is covered with the proposal that we have today. So between 2014 and 2016, Matoush was trying to standardize his library and got multiple versions of the proposal paper. And again, this is a library focused on type traits and metaprogramming. And in 2015, we had Boost HANA by Louis Dion, which implemented this library that also tries to reflect on the code, again, using template metaprogramming. And at that point, it became clear that template metaprogramming is not a great tool to do reflection on programs because it's very heavy on the compiler to be able to extract the data from. So we basically abandoned or left the idea of using template metaprogramming for this and went leaned toward the idea of using a specialized syntax. So we had a new syntax for reflection discussed in multiple papers. Thank you to Matoush, Axel, David, Senkel, Andrew, Herb, David van der Woede, Louis Dion. All of those people were contributing quite significantly to exploration of this design space. And we had something called meta objects emerging around that time. I will get to that soon. But meantime, try to think about what reflection is trying to do is basically represents your program, and try to think of how would you write a program to represent a program, and we'll get to that later. So in 2018, you can see there was another paper that tries to set the direction or the usability of the feature by Bjarne Stroustrup, and you can already understand that there was a lot of interest. There was also a publication of the reflection TS. TS is a technical specification by David Senkel. Again, a document that basically set the ground for very syntaxes not far from what we have today, in some meaning. In 2018, we had also discussion on value-based versus type-based reflection. And I want to go back to what I mentioned about meta objects. So if I want to represent something in the world, in a program, natural thing to do is to represent by inheritance. So let's say I have a function, I can create a base class called function, or represents a function, and I can inherit from it to represent a static function or a member function or something along those lines. But it turned out that representing our program in that way is going to be, again, heavy for the compiler because there's a lot of different types that can create a burden for the implementation. And implementers basically have ask or push toward having what is called a value-based reflection. So the idea is that instead of us having this hierarchy of types, we're going to have a single type, which is what we know today as the stud meta info object type from the reflection proposal. And this would be representing all the different entities in our program, functions, types, variables, etc. Even values, const expert values, of course. And in 2019, speaking of const expert, we also had more discussion on const expert. And const expert generally have been extended, abilities of const expert have been extended toward the latest standards of C++. And I think it's awesome. C++20 have already enabled a lot of const expert abilities, or extended farther more context variabilities from comparing to previous revisions. And I always say that C++20 is a revision that is very helpful for embedded and other restricted environments. And one of the reasons is that we can do more things in compile time, but we've even extended farther. And you can, of course, search for Hannah de Sokova, which, by the way, I don't know if I mentioned before, is the chair of ST7, the group that is in charge of reflection. And she already extended a lot of our standard library to be supportive of evaluation in const expert. So that's pretty awesome. But again, going back to const expert and just in the context of reflection, we also know that const expert by itself is not enough to basically express all the syntax that we want to express in reflection, and that's why we have a specialized syntax. So as always, for proposals and features, we had some discussion on naming and on syntax itself. And that was throughout the years. And we had in 2022, again, discussion on value versus type, where we landed on value strictly. And because of some newer discussions on reflection, as you can see, this have been worked for a while. And in 2023, we had the proposal that was voted in Saturday, P2996, reflection for C++26. So again, I want to thank to the authors, Barry Resvin, Wyatt Charles, Peter Dimov, Andrew Southern, Faisal, sorry, I don't remember his last name, and David van der Voorde. And also I want to mention here Dan Katz, which is implementer for Clang and also been contributing a lot to this proposal. He became author in a later stage of the proposal, not in the initial stage. You can also see his name here on other papers. And because of, due to those people's great work and also providing the implementation, and again, Wyatt also did this for EDG, we actually have the feature. So yeah, we're now 1.5 years later, even a bit more, and the proposal revision that was actually voted on Saturday was R13, I think. But here you can also see Dan Katz have joined as co-author at some point, and thank you very much for all those people for their hard work. And I also want to point out that after the proposal in 2023 came out, there were different papers trying to look at the syntax as proposed and basically evaluate it for different use cases, for common use cases for reflection. For example, Python bindings or JavaScript bindings. And I'm really thankful for Adam Jagut, authors of those proposals as well, for doing this evaluation, which is very helpful. When we propose a feature to the standard, we really try, it's important to make sure that, that its usability is fitting for all the use cases. So papers like that, evaluating the usability, are also very important, almost as, or even as important as the original papers proposing the feature. So thank you very much for all those people. So what do I mean by reflection? So I've talked about the high level of reflection, and I wanted to show you a bit of example that you'll have the syntax in mind and understand how it looks like. So we have a class here, libtype, and it inherits from base 1 and base 2. Here you have members, of course. And here in main, I'm trying to evaluate. This code is basically trying to do the most basic thing that you can do, of course. So it's a simplified one, but you have reflection. You take the libtype and you lift it into reflection realm. So when I say lift it, you can think about those two domains as two separate aspects, or like a mirror world. We have the reflection realm and we have the C++ program realm, and we try to move between those two in the syntax. So we're lifting libtype into reflection realm, and we initialize this expression that captures the libtype, and it's actually an expression of type std_meta_info. It's a std_meta_info object, as I mentioned, to represent entities in our program. And now we can call the function metabases of to extract back from this reflection expression. And what we're going to get as the return of bases of is a vector of std_meta_info objects that contains base 1 and base 2, which are the bases according to the order of declaration. And of course, when we get to the first element of this, we're going to get base 1 as expected. Cool. So reflection proposal have different parts, and I wanted to highlight those parts for you so that you can have better understanding of what we have there. So we already talked about the lift operator. And next thing we have is splicers. We also have the std_meta_info object that I mentioned, and we'll look into that with more details. And of course, we have a bunch of meta functions. So the functions, the meta functions are, if you can look at those, some of those names, they resemble, some of them resemble things like type traits. but we had a lot of discussion on whether we want to add those in the reflection namespace as well, or some of those that might be duplications or pure duplications, but those are actually able to be supported by compiler intrinsics. We also, some traits are also supported by compiler intrinsics, but this could potentially provide a better performance and also fit to the other const expert aspects of this proposal. So you have here a bunch of functions also, because this is an updated talk, and I gave this before, but I wanted to update to the latest state. There's some of those that were removed due to complexity or other issues that were discovered, but there's nothing prohibit from us extending this proposal in the future. So it's already quite extensive toolbox, but we can always add on top of that later. And yeah, and I think it's pretty awesome. So okay, let's go over the details. So we have the reflection operator lift, and it used to look like this with a single operator, but today it's a double operator. If you want to use the nickname, you can also use the nickname Unibro. This nickname was created by JF Bastin, which is the chair of Evolution Group. I mentioned Evolution is the group that is in charge of the language, and we are in charge of the standard library. So yeah, only don't forget to give credit if you use this nickname. But of course, you can also use the more formal name, which is the lift operator. So we have here an int, it's type, and it's being lifted into the reflection realm. And we initialize this expression. But even here, and again, we're shifting from the C++ program world into the reflection world. But here, we're already going to get an error. And if I could take your hands, I would probably someone would have spot that. But I already said that in the beginning, in the intro of the talk. Keep in mind that what we're doing here is a static reflection at compile time. So the compiler have to be able to hold this information and evaluate it. So naturally, in this case, we're going to get an error, which is that the meta type must be const expr. So here, we actually cannot execute this line. Instead, what we want to do is decorate the reflection expression with const expr, and now we're golden. So yeah, we've lifted int into the reflection realm. We captured this with a reflection expression. Int is a type, of course. And now we can move to the second part, which is extracting from this reflection expression back into C++ realm, back into our regular C++ program. So ignore this. I can talk a few words about this later, but basically we have here the splicer operator, those two on both sides of the reflection expression, and we extract the expression back into the C++ realm here. So just a few words on type name. Type name is what we use to disinvade ambiguous names. So if, for example, I had potential for ambiguity, let's say if I had a namespace also, and I want to emphasize to the compiler that this is a type, then I can use that to disambiguate. And you can read more about this in the proposal itself. But yeah, so as I said, we lift into the reflection realm with holding an expression for it, and then we go back into C++ realm by extracting this expression. And we can use that in a C++ program. So let's do a little riddles here. What is this reflection expression? Right, so we talked about we take int and we lift this. And we already said before, reflection expression is basically a stud meta info object that contains information on this int type. So this is not an int, but it's a reflection of the int held in a meta info object. And what is this type name again, or even if you ignore the type name, what is this spliced of the expression? So again, we said this takes us back to the C++ realm. So now it's been extrapolated to an int. So this is actually been this is actually an int here, and what I do in line 2 is I declare int a equal 42. So of course, this is a small example, 2 lines, but keep in mind that even if if reflection expression is something that I got from externally or from a different piece of the code, and now I can create an instance of this type here without knowing exactly what it is. Of course, I have to know for initializing, but generally speaking, this is a very powerful tool because I can keep a expression that represents something, and then I can extract it back into the program and create instances of this thing in my program. So we talked about reflection operator and about splicers. Let's talk about a bit about stud meta info. So here I have a piece of text. And again, if I could take your hands, for those of you who've studied compilers course or been uh, advanced users of Clang compiler might recognize this as the abstract syntax tree of Clang, AST. And this is indeed the way the compiler is looking at programs. So AST is, let's say I have a C++ program and I have the front end of the compiler. It parses the program. It's basically creating this model of the program with hierarchy that represents my program, the text that been parsed. And now this AST is being sent to the backend of the compiler, and the backend is basically lowering this AST into binary, into bits and bytes. According to the platform, of course, in Clang's case, it's LLVM. So according to the target platform, we're lowering this model of the program to the bits. So to binary code. So here we can see on the right the int main, and I have int I equals 0 declared. So you can already see in this up to syntax tree, function declaration, variable declaration, I, which is the name, and int, which is the type, and even the fact that int is L value, etc. Sorry, that I. But basically, this is very similar to what you'd expect to have for reflection held in stud meta info, and that's not a coincidence. So stud meta info represents type and type aliases, functions, variables, static data members, structured binding, non-static data members, enumerators, objects, etc., expressions, constant expressions, and values with structural types, permitted result of constant evaluation. So this is important. I'll get back to that in a second. Template, namespaces, and namespace aliases. So here I have an example again, and note those lines. We used to allow constant expressions, but it turned out that constant expression, just allowing constant expression, is quite complex. There's a lot of edge cases and usabilities that this covers, and we had to narrow this definition to only objects that is permitted result of the evaluation. So of course, again, as I mentioned, we can extend things in the future, but this is where we landed now. And this boils down to the fact that let's say I would erase this const expr here, then I have an int a equals 42, but then I cannot evaluate this value to reflection realm. So again, remember before that I was talking about the const expr, the reflection expression represents the object have to be const expr. Now I'm also talking about the value here because in the previous example I talked about the int type, but here I talk about the a variable. So the value of the variable itself have to be const expr. And then we can lift this into reflection realm, and that would work. So again, keep that in mind when you think about reflection. And I think the key aspect that you need to take from this is whether the compiler is able to look at this thing at compile time. So we talked about stud meta info. I also wanted to highlight some more unexpected or unintuitive aspects of how meta info works. So I have here a class R, and this is declaration. And I have here res which is, so I lift R into reflection realm and I capture this in this res1 expression, stood meta info, of course. And then I can give this res to the stood meta function is complete type. So for those of you who are not familiar with the term, in C++, we can define and we can declare and we can define. So in line 4, this class is only declared but not defined. So the question of is this complete type will result with the answer no. False. This is not a complete type because the compiler at that point in line 7 does not know how to instantiate this type. Then we continue and give the definition of the class. So we now have a class R with a member, and we know it's now a complete type. We know how it's defined. And we take res2 and we lift R and we have this expression to evaluate. So of course, in line 15, the evaluation is going to be true. So we have false and we have true. And now my question to you is, what happens when I try to evaluate res1 that I took here on line 6 and try to evaluate this in basically in line 17? So there could be two possible answers here. So we said we have false and we have true. And then the question is what gonna be the third expression. And it can either be true or false. So I guess I could take your hands. Again, as I'm not there, unfortunately, I can't. But previously I tried this. A lot of people said false. But honestly, what's gonna happen here in line 24 is that we're gonna get true. So it might be a bit surprising. But again, the reason that this happens is because despite the fact we're taking res1 here in something that looks like a value, looks like a snapshot of stood meta info, in fact, reflection, the way we got this in 26, the way that the feature is in 26 is that, sorry, this is not a stateless reflection, but a stateful. So this, despite looking like a value, is actually more like a reference to the AST. And once this the state of this object of class R is updated, res1 is now representing the updated state of this class. So again, when I say, or important to me to emphasize, when I say a reference to the AST, it's not necessarily how the compiler is forced to implement that. When we talk in the standard on features, we only talk about specification and semantics. We don't talk about the implementation. But at least when you have the mental model, you now would understand or be more accommodated to how this reflection works. So yeah, false, true, and true. All right, so we went over the lift and the splicers and the stood meta info object. Now we're going to briefly talk about the meta functions. So as I mentioned already, there's quite a lot of them. A lot of them resemble traits, but can actually be improved. And let's look at this short example. So I have here again the context per auto variable declared, and I can execute a name of on this of lifted the reflection expression that represent it. But in C++, name is ambiguous because we could have fully qualified name, etc. So we've decided to modify the name of this name of function into identifier of. So now we have something that is less ambiguous, and we also leave the design space for later to come with things that are more context-based names. But identifier of the lifted A would return A as expected. So this line would print A. And all of the meta functions except info, or apart from a small, just a few that takes reflect value that takes type T, value object or function that takes type T. But generally speaking, except the info, meta info object, as I said, the result of lifting things into the reflection realm and return either string view or stood meta info object, a different one, or a vector of stood meta info objects, or a Boolean size T, T, which is the type itself. For example, for extract can take a stud meta info object, so the reflection representation of something, and return the T, the type itself. And source location, member offset, those are structs that we created especially for offset of for bits and bytes, etc. So let's look at two interesting functions in reflections. I think I find very interesting, and also again emphasize the way reflection works. So we have substitute, and substitute is the equivalent in the reflection realm for instantiating a template. So we have here example. We have reflection expression that captures the result of substitute. Of course, it's from Student Meta Info. It's a shorter version for slides. And I give it the reflection of a template, and then I give the put as second operator list of template params that the reflection of template params that can be used in this template. So in this case, array can get an int and 3. Of course, the value reflect value. This have to be reflect value of 3 because 3 itself, as we said, is you need to lift this into reflection realm. So you need to put here student meta info, and that's exactly what reflect value is doing. And now I can instantiate the stud array with int and 3 and get my array, which is basically the expected type. After I spliced it, of course, put it back into the C++ world. But if you look at the second example and imagine here that's even reflect value, ignore the 3 by itself. Let's say I take a different structure of some templated class declared here, and I again pass int and reflect value of 3, let's say. And let's say the S cannot accept those parameters as the template params. Then in this case, we're going to get a failure when we try to extract the reflection expression back into C++ realm. But it's important to note here that we're not going to get the failure when we try to substitute. We're going to get, when we evaluate this expression of substitute with saving into reflection expression, but we're going to get the failure when we try to instantiate, because that's like a delayed instantiation, right? It's here we only capture the information, and here we actually execute according to execute the functionality. Another interesting function that I already mentioned and briefly talked about when we talked about meta objects and metafunctions is extract. So extract is doing something very interesting as well. It's trying to, it's basically taking a type. It's a templated function. It's taking a type and it's trying to extract from the stud meta info object that it takes the value that can be fitting into this type. So here we have a reflect value of 3. So we already said reflect value is being used to provide a stud meta info object that represents 3, and 3 fitting for int. So that would basically work, and we can extract this expression. But when we try to do the same thing with something that doesn't fit the type, for example, here reflect value of the string 3, or char pointer, depends on which world you're used to, this would fail, right? And it will fail in the extraction because now we can evaluate. All right, so we talked about interesting functions, and I want to give a bit more focus on the type traits that we're going to get in reflection. So type traits in general belongs to two realms. We have type trait that query the type, basically returns true or false, a Boolean, and we have things that modify the type, like remove CVRef. in C++ standard library in general, right? Not just not in reflection even. So 2996 have focused basically on the first type mostly in this revision, but I really think it's interesting to think about which functionality can we get as part of the standard library for the reflection traits that are doing things that are more complicated, like modifying or giving us different results. And I think that I expect that in the upcoming years, we're going to get more and more of those. Okay. So now we talked about reflection. We basically covered all its different aspects. And I want to talk about a bit of a different paper, 3096 by Adam and Jagret, that I mentioned in the beginning of the talk. And this paper is trying to talk about another kind of edge cases or unexpected result of reflection. So let's think about function declaration in C++. So we have function declarations, and they can basically, and when I declare a function, I can basically use whatever names of params I want, of variables, sorry, and and I can do this differently in different declarations. So here I have a function that prints the param names of a function that it takes. It's a metafunction or a reflection function that prints the param names, and I give whatever like specific the specific location in the array. And then let's say I declare a function func with int first and last param names. And now I call my print function here and print the param names. So here, of course, we expect to get first and last after the first declaration. Then I declare this again, and that actually a valid C++ code, right? I can define the function, sorry, again. And when I define this, I define the function with different param names. So now I have what used to be first and last is now n and ln, for example. And when I call my print func param after the definition, I can get a different result. So on the first one, I'm going to get first and last, and on the second, I'm going to get n and ln. So this may appear, I mean, it makes sense, but also if you think about the usabilities, use cases of reflection, you think about things like logging or trying to basically capture the structure of the code. And if we get different names because of the different declaration names in the declaration and definition, we may have inconsistent. Also, you might think of different how different results that can be for those evaluations, right? So yeah, the paper P3096 have explored this design space and all the options that we have for addressing this. So we can do different things. We can basically, in the case that I've shown, we can compile and make no guarantees. So maybe different, if you use different compilers and you run reflection, you'll get different result. Maybe one compiler would take the names from the declaration, and one compiler would take the names from the definition. So we might get inconsistent output. We can enforce consistent naming. So basically, we say the code that introduced different names for the declaration definition would not compile unless the names, unless the names are the same. But if you think about this, it's very interesting in philosophically wise, because in C++ language, we do not have this kind of enforcement. We allow different names in declaration and definition. That's actually something that is used in different code bases sometimes, either because we want to give context in the definition or in the declaration and use different names in different contexts. So we basically add additional requirement for those code bases to be able to compile with reflection. And third thing we can do is mark by attribute. So basically we signify this names, let's say, for example, for this declaration, those names are what we want to see, like canonical names. So yeah, this is basically what we've been exploring, or what the authors have been exploring in the paper of function param names. And we ended up with the enforcement of consistent naming, or in another way, it's if you don't have consistent naming, your program will be ill-formed. And I think that's actually a reasonable compromise, because on the one hand, you avoid inconsistency, and maybe might mean that your logger would not work without consistent naming. But on the other hand, you get the consistency in terms of, like, if you execute on different files, etc. On the other hand, think about your code base that you already have, and you now introduce a logger library that relies on reflection, and this logger can use on some parts of your code base, some projects, let's say in a company, but on some other projects, it will not work. It will simply not compile because the inconsistent naming exists. And again, this is not something that we've limited in the C++ world, in the functionality world. So I don't have enough time to go over this example of reflection logger, so I'll encourage you to look at this later. I do want to talk briefly about customization points. So customization points are a mechanism on which a user can basically provide their own implementation to a library. So libraries, generic libraries, can do things in certain ways, and sometimes the user have additional information on how things need to be done for their types. For example, swap is a very common use case on which you can specialize the way your type is swapping. So there's different ways to do customization points. One is, for example, virtual functions, or template instantiations, or a functionality detected by ID like swap, as I mentioned. And if you want to learn more about it, feel free. I gave talks about this topic, same talk in multiple places about this topic. And this is actually based on a very good paper from Barry Resvin that tried to explore this. And I would encourage you to go and watch those to learn more about customization points. But one of the options that were in the paper, and option for customization one, was reflection, because with reflection, you can basically break apart the code from the library and rebuild this, for example, in the way that fits the user, or inject things into the logic. So yeah, reflection was brought up as an option. But personally, I think that it's a heavy tool for this kind of usability, because we, as library writers, we don't want our users to have to break our code into parts in order to basically opt in to their type, or give us the additional piece of information of the type, of their own type. So I consider this a feasible tool, but still I think too much of a heavy hammer for what we're trying to do. And therefore, my view for the standard library is that I think we need more abilities to do customization points. And this paper was, or this discussion was, a few years, basically before reflection was published. It was trying to aim to the what we think that's going to be the reflection. Now that we have it, I can say the list from my part. I think that reflection is too much of a heavy tool, and we still want to explore other customization point mechanisms for the standard library. So yeah, again, I don't have enough time to go over this example, but just think about the ability to customize into your type. And this is just an example from one of the original reflection papers that basically breaks library type into basically by iterating over the data members of this type, and rebuilding this rebuilding, let's say, user type based on the structure of the library type. So we could basically break apart all kind of structures and build your own structures based on them with injected functionality. But again, this is an example that in my mind shows that this is a heavy tool. We not necessarily want to give our users this functionality. Of course, when I say users, it can be other libraries as well, right? It doesn't have to be like the end users. And yeah, this is from the paper from Andrew Saturn. So few more points that I wanted to make on how reflection can be used. So I already mentioned the function param names, and you need to think about what happens when we have different names. There's other interesting aspect of reflection, which is that we can actually reflect on the private members. So we are used to having, access modifiers basically signify the limits between different codes or logic. So if I have a library code, or if I just write my own class for someone else to use, I can have my private members, and I can, in a sense, I draw the line between the implementation details and the API, the interface, the public interface. But the fact that reflection allows us to access the private members is actually kind of breaking the line between the public interface and the internals. And that's actually very important, for example, for the standard library, that is the reason we've explicitly specified that reflecting on parts of the standard library are not stable. So basically, we're preserving ourselves the right to modify the implementation details in utilities that are in the standard library between versions, or even within the same version. Like if we deliver some, so as you probably know, in C++, we try not to break API or ABIs, but we can actually change the implementation detail of structures. And when you, and by the way, it's basically discouraged to reflect on standard library types. But generally speaking, even if you would have done this, you need to know that there's no guarantees. Because of this, because of the aspect of reflection of breaking the boundary. And one more thing I think we need to think about is what happens when we get new code. Let's say I have a code that fits into the requirements of this logger that I mentioned before with consistent names, but then we get new code that someone goes into my code base and modify this because they just are not aware. And now we're basically not compiling with this logger library. So all of those things are things that we need to think about. And to summarize those aspects, we have a pipeline of reflection when we give used to, or at least the normal pipeline without reflection is we have a logger library and we compile this into this object, and then we can link this with our application code, with the main, for example, in the linker, and get the main program. And we can use version and macros in compile time to basically choose between implementations. And all of those things are things that we're familiar with. But in reflection realm, we can have this logger library, and if it's written in reflection, and we link this, not link, we including, because we have to have that available at compile time, to our application code. But now the point on which we're going to get the failure is on the compiler and not on the linker, as we may have been used to. And that also is important in aspects of all kind of systems that replace dynamic libraries and things like that. These are different ways of constructing our code that we need to take under consideration. And that's actually interesting aspect of reflection that we need to think about backward compatibility. So I have just a few minutes, and I want to briefly talk about AI. So as I mentioned, I'm in Microsoft, and I'm sure you all heard of ChatGPT and Microsoft are really keen and excited about AI. And I was wondering whether AI can actually replace the need for the reflection feature, because what we're trying to do here is things like parsers and kind of code generation. And AI can actually generate code, and technically I could give it my source code and ask to generate parser. Um, so I did try to do this experiment, and I gave this type, and I've asked to generate serializer for my type, etc., as you can imagine. And there were multiple things that I found when I tried to do this. And again, all of those things are talking only about AI as it is today. And of course, that this world is updating really quickly. And by the way, I'm also part of a team in Microsoft trying to work on extending developers' tools and giving to developers more tools of using AI, etc. And fitting that into the developer workflow. But for example, the first experiment gave me different return types from the serialized and compared to the input type of the deserialized, which if I would have write this code by myself, I would probably look for consistency, let's say go with a vector. Second aspect of this was that the functions themselves, the read from the serialize and deserialize, basically the implementation detail, we're using memcopy, which is okay if I have structural types. But let's say I replace or I add member to my original type, and I need to call constructor and factors, so this is not working. And the third issue was that basically we have here deserialize function, and if you're looking, we basically return my type, but from the buffer. But if you're looking at the code and this implementation, we always get my type back. The only question is if the parsing failed is whether we get the members initialized or not. So of course, here also we need to basically know to do the error handling in this type, and this logic is faulty. So to summarize, my points are, by the way, I tried also to do this second time with the first project to see if there's consistency. And as you probably already know, as some of you, I'm sure, have already worked with AI, there's no consistency between those two experiments. So in the second attempt, I can get a completely different issues or bugs in the code, etc. So to summarize, I think that AI can definitely be considered for those things. But the point of AI being non-deterministic and in a sense by design, providing different results or different solutions is one of the reasons we might still want to keep code generation and features like reflection that are deterministic, that are always giving us the same result, assuming no bugs, of course, expected results for what types of structs that we gave. And I think that is the powerful part of features like reflection or other code generation features like Jinja, if some of you may have heard of, which is basically a Python framework that you can give like a template of a code of a file, for example, and generate different versions of this file, extracting those templates. So not in a C++ term, but templates in term of patterns. So my view is that we still need those deterministic frameworks. We still need this feature. But who knows? You know, everything changes so fast. So maybe in a few months, AI is going to be powerful enough to give us consistent result. And let's see. Second thing I wanted to mention is Rust. So Rust does have a toolkit for reflection. It have macros and it have the sing library that basically injecting tokens into the AST. We already looked at the AST before. But we can use this to inject things, which basically means modifying our AST of the program and creating new parts of it. But I think that, in my opinion, injecting into the AST, and you already seen the complexity of that, it is forcing the users to know more about the basically the underlying implementation. And this is something that we probably as a community should discourage when you start mixing logic of the implementation and into the logic of what you're trying to achieve of your application code. That might create that's not a good it's not a good way to write language. So in my opinion, our reflection is still more powerful and cleaner. And actually people from Rust, I guess agree with me, because there's some blog posts exploring what C++ is doing for reflection and trying to compare to that, or trying to look at this. And as a first result, as far as I could find at least, there was an improvement suggested to the Sing library by cleaning up the need for users to address edge cases and things like that, and making this more usable. But still, this is still a library that modifies the AST, so it still need users still need to understand those concepts in order to use it. Okay, so to summarize, what should we expect from reflection libraries? I think we can gonna already expect some very interesting use cases, parsing, etc. But we need to keep in mind that there's no compatibility between standard versions and no guarantees for existing code. So reflection can be modified, and of course don't reflect on the standard library. Possible outcomes is that your program is going to be ill-formed, or you can maybe get UB and other things. So we really had a very interesting discussion on how do you reflect quote errors from reflection. And actually Hannah Sokova, which I already mentioned as ST7 chair, and by the way also evolution co-chair, she came up with compile time exceptions. So we can now have context pair exceptions. This is really awesome. Those are basically can't be thrown. So during the compile time, during compiler execution, it can throw exceptions, so you can get the errors from the compiler, but those cannot leak into the runtime. So those are only limited to the compile time, but these are pretty awesome because they give us better indications. And by the way, it's not only for reflection, it's just a tool for better warning and better indications, better error handling, error reporting. And maybe in the future, we might want to consider warnings as well. So thank you very much for listening. I would love to hear from you which reflection libraries you think is going to go into the standard library. And maybe you'll come up with very good use cases now that we have this feature. And I would also encourage you to go and look into those talks and papers. By the way, Daisy Holman, she's a Workgroup 21 member as well, and she gave a very interesting talk about AI and how it works. So if you want to dive deeper into that, it was in ACCU 2025. The slides are here. And so I just want to emphasize again the time that it took to get to this feature, but I think it's a great feature, and I'm very happy that we finally got this after all those years. And thank you to Core CPP user group, to Hannah Sokova, as I already mentioned, her great contribution. Matush, David, Sankel, that I've talked with to get additional input on their parts of this, and Corentin, Luis, and Adi for reviewing early versions of this talk. And of course, to all reflection paper authors. And thank you for listening and for being passionate about C++. And please feel free to reach out to me. Thank you very much, and stay in touch.